Also, the first lecture that I just did, the recording for that is already linked on the syllabus. So you could see that, or you could eventually see this video. I think they'll be pretty much the same. And a lot of times I'll post the second video for the second lecture, you guys, because it's usually honestly a little bit better, even though I've done these lectures. So, but sometimes the second lecture just, removes a couple of kinks that might have occurred the previous hour. In any case, so one major announcement. Of course, we have our final exam coming up.
Just finished.
Uh, so in case you haven't seen already, the link to the breakdown is on the syllabus, but I also sent out an announcement with that link. So if you don't get it between those two, email me and definitely let me know. It's 100 questions. There is a good amount of kind of the X-ray physics stuff on it. So someone asked in the last class, is the test more towards the first half of the semester versus the second half? I would kind of say more the first half, because there is a good amount of like general kind of physics questions, like, what happens when MA doubles to the intensity? What happens when you change KV? How does, thermogonic emission work and MA? Well, a lot of those kind of questions are on there. And you have 2 hours to do it. There is a seating chart, so we will know where to go, myself included. I'll be proctoring, I believe, with Professor DeVito, who you met, I think, maybe only once during orientation. You would have him as senior students. Next fall, though, I don't think you have him in the spring for anything. Hopefully, so that's my major announcement. I also sent an announcement today with, and maybe I hadn't sent it before, a breakdown of some questions from quiz 4. So please take a look at the announcements on Brightspace if you haven't. But everything is done. My spreadsheet for all the grades, the only column that's missing is going to be the final grade. So everything is put in there already. Everyone automatically got 100 on lab quiz 2. Everyone's getting the full 5% for participation. The college is so wishy-washy. I really don't understand them. They say we're like a non-attendance taking college, but then they kind of want us to take attendance, but then they take our tool away, but then they say, okay, use the old tool. Anyway, they go back and forth. That said, you'll have 2 hours for the final. And that's about it. Hopefully for clinical, you are getting yourselves cleared. It's a process. And in some institutions, most of them, it's not easy. And at the same time, as much as the X-ray departments love students, they really do. They love us. Not so much for human resources. We don't seem to take that high of a priority, and people are going on vacation and it's holidays and it's just hard. And trust me, I just made 2 or 3 different doctor's appointments today. It is very hard to get. I mean, I have one doctor, uh, February 3rd, I think is my appointment. I'll either figure out what I have or just be dead by that time. So it's kind of crazy. So if you have to go to urgent care to get some of this stuff done, I'm going to urgent care tonight because I can't get an appointment with like a real doctor. Not that they're not real, but um, it's just, and of course it's more expensive. So that's me. Hopefully I will eventually, get better. So if I cough, I cough. What can I say? So short lecture. A lot of this stuff you will probably know. Before I share any questions before we get into anode heel effect and other things related to the anode, like focal spot and penumbra? We're all good? Okay, let's do it. Let's see, hold on. This time the recording button is on already. All right. Okie dokie. All right. Yeah, I don't know how I showed up last week and kind of dragged myself. Um, Having a persistent cough is tough. And this is worse than like COVID. And I had COVID twice. But the anode bevel and the focal spot has not changed. And I know that stuff like the back of my hand. And you will too by the time you graduate. That's for sure. So a lot of this is not new information. I'll try to bring out some of the newer stuff and spend a little bit more time on that. The actual angle bevel, which you don't even have to use the word bevel, it's just the angle of the anode tube, is what really determines, especially when you add in the size of the actual focal spot, it determines the size of what we call the effective focal spot, which is always like 10 times smaller in many cases than the actual focal spot, which, as you might remember, is due to something known as the line focus principle, which we go over again in this lecture. But we can look at the angle as a line drawn from basically the end of the tube to the anode down here. And this is our angle. And we're going to see the size of that angle has an effect on the size of the effective focal spot. Actual focal spot doesn't change other than if you switch from small to large focal spot, then you're changing the actual focal spot. Larger if you're using the longer filament, smaller if you're using the shorter filament. And we should know, because this was our second or third lab, where we broke out our test tools, I think, for the first time, that when we change the focal spot, it's going to have an effect on spatial resolution. Typically, hard to see that effect unless you magnify a lot on the actual image, but we were able to see that the difference between a small and large focal spot was the difference between a small focal spot having better spatial resolution, meaning higher sharpness, technically ability to resolve smaller objects, because if there are objects that can't be resolved, then essentially it's as if they weren't there. And if that's pathology and you can't see it, then you walk out with a negative result on your x-ray and you feel pretty good about it. There are other exams, other modalities like nuclear medicine that, in kind of quotes, see things at an atomic molecular level beyond what you can in x-ray and in CAT scan. But we can only do so much. And we know that a larger focal spot will not give us as good resolution, and that we'd rather not use it because we have more penumbra, so we get more blur. That's why the sharpness goes down. That's why spatial resolution goes down. We need to use the large focal spot if we have a larger exposure. So if we're doing Bucky work, so some a hip x-ray or spine or skull work, right? Because those require more exposure, if you were to do that with a small focal spot, you run the risk of snapping the filament, right? That smaller filament, less lengthy filament, will take longer to boil off the electrons you need to give you the photons you need. So that's why we'd rather not use the large focal spot if we don't have to, because you give up a little spatial resolution. So that blur, right? This is a word that you now know, right? Maybe you didn't know it a year ago, unless, as I told the last class, you were, listening to some information about the solar eclipse that we had in the summer, which was pretty cool. I personally went out to the Queens Science Museum, and they had a nice little setup. They gave everyone glasses, and they had music, and there were lots of kids. Took my kid too. It was good. But the sort of edge of light around the sun, they call that penumbra as well, also related to the corona. Anyway, I'm not a astronomy person per se. So our penumbra, though, is the blur that we have around an object. And we can say that the focal spot not only has a relationship, but it's directly proportional. In other words, if the focal spot gets twice as large, your penumbra will double, right? Also, of course, works conversely, right? Smaller focal spot will give you less penumbra, which is why we want to use that smaller focal spot. Again, some of this in reality is very hard to actually see on a radiograph unless we kind of magnify everything. On another note, I'm looking forward to next semester, as I always do for the spring semester, because at that point, you guys are in clinical, you start to tell me stories. We talk about some of the things that we're learning about that have where you see them in action, and then there are things that should be happening that aren't happening, and that's always not so great to hear, but you get a taste of reality. So that is definitely coming up. You should be looking forward to that. The actual focal spot, and guys, please raise your hand or just unmute yourself if you have a question as we go. I do have a hard time seeing the chat, so that might not be the best way to ask me a question. So actual focal spot. This is the part of the tube. Oh, okay. Yes. What is your question?
Yeah.
Richard?
How you doing, Professor?
I could be better, but not too bad. Excuse me.
Yeah, my question is, you talked about large focal spot and smaller focal spot, how it affects the penumbra. So I wanted to ask, does SID or moving the tube, does it also have effect on the penumbra?
It does.
Okay.
Yeah. But it's more about, I don't know if it's a direct or indirect effect. What I can certainly tell you is, and the textbook will also tell you that as you manipulate SID shorter or manipulate OID larger, you get magnification, which is a form of distortion, but essentially boils down to your spatial resolution going down. So I don't know if it's the spatial resolution goes down because it creates more blur exactly. But we can certainly say that both SID, OID, and focal spot all have an effect on spatial resolution. Whether that vehicle is specifically related to penumbra, I don't know if I can say that 100%. Right. I know we can say, like, when you magnify an image on a monitor, right, it gets bigger, but the resolution goes down. Is that due to penumbra? I don't, it's a little different.
I think when you move the object closer to the tube, there's more shadow, there's more penumbra than when it's closer to the eye also. That's why I asked the question.
Yeah, I think there's a better argument for OID changes than there is SID. Because when you have OID, you are kind of changing. A lot can happen with the X-rays coming out of the patient, like the remnant beam and that space because of the OID that you have with the image receptor. I don't know if you can quite say the same exact thing for SID. Okay. Actual focal spot is the part, right, that is literally bombarded, right? This is the part that creates a lot of heat. This is the reason why we do many different things to mitigate that heat, like spinning it around so that we can kind of not literally hit the same spot all the time. We add the oil, we add the fans, and I believe, the whole process is really inefficient. We get, I believe it's 99.4% heat and only 0.6% X-ray, something pretty close to that. But we still get quintillions and billions of photons, so we get enough. Ironically, many of those get stuck in the patient as well. But it's the actual focal spot, right, that has the heat problem. The effective focal spot, you can't even really touch it. It's not physically present. The effective focal spot is more theoretical. It's said to be viewed from the perspective kind of looking up, as if the image receptor had eyes and could look up, right? We can say that the effective focal spot is always much smaller than the actual focal spot. And it's pretty small, around 1 millimeter. We'll see in a couple slides from now that we can actually get down to maybe 0.5 millimeter. But that effective focal spot will change based on the angle of the anode. And the rule here, so this is the part that's underlined, right? As the anode angle goes down or is reduced, the effective focal spot gets smaller, right? We're going to see that. Is it the next slide? Right here, yeah. So you can see, here's our effective focal spot. But before we point out what's going on here, notice that the beam of electrons, this, what we call the cathode ray beam, is the same for both of these anodes. The difference here is that the anode on the left, even though it looks steeper, this angle in here where I'm kind of moving my mouse here, that's 17 degrees. Much less than the angle here, which is 45. And it's that angle, or what we call the bevel, it's that angle that gives you the much smaller effective focal spot. And remember, spatial resolution goes up no matter which focal spot gets smaller, right? So if we reduce the actual focal spot, spatial resolution increases. If we have a steeper anode, which we can't control, right? You purchase whatever you get, you can't manipulate it like a seesaw. That would be interesting, and I've never heard of anything that does that. But on average, you'll also see in another slide coming up, we average around 15 to 17 or 18 degree anode angles. We can get smaller in some units, like mammography units, where you want a higher spatial resolution. You can get away with using a smaller focal spot because you don't need to create as much radiation, right? Yes, breast tissue may vary, but the variance is not the same as the difference between doing a wrist and doing a lumbar spine, right? Even if you have the difference between what's known as dense breast tissue versus less dense, right? It's not going to have as much variance. So you can get some units out there But in a general X-ray unit, we're averaging around 15 to 17 degrees. The smaller, as it says here, the smaller the effective focal spot, the better the spatial resolution. But that also goes for the smaller actual focal spot, right? However, right, if we utilize a very small actual focal spot, that's going to create too much heat. It's kind of like if we get it down so small that the cathode ray beam is like a laser, then we're going to have a problem with heat, which could melt our tube, melt our anode, definitely reduce the life of the equipment. And if we're using a very small filament to get to that small actual focal spot, we run the risk of snapping that, especially if we try to do exams that require a larger exposure, like anything in the bucking, like skull work, shoulder, pelvis, etc. But again, in a unit like a mammography machine, where you're limiting to a certain body part, then you can have sort of a niche unit that only uses smaller filaments, leading to smaller actual and effective focal spots. So you might be able to get down to like this 0.5 level down here, maybe even just a tiny bit less. But you'll see, we could have a problem if our pixels are too big. But we'll talk about that in a couple of minutes. Questions? Everyone okay? Chris, I appreciate your video on. Everyone else is afraid. Either that or everyone else has a really bad hair day today. I know it's raining and
I have a bad hair day today, and I still will put on my video.
Chris, turn
I
off
didn't
your
want-
camera right now.
Don't make me laugh. It makes me cough, guys. Okay. It literally does. Well, I appreciate it. All right. So, on average, a large focal spot is going to be somewhere around 1 to 2 millimeters. And a smaller one can be 0.5 to 1. I mean, if you take the extreme of one and the lower end of the other, so if you take the 2 versus the 0.5, you can get 4 times better resolution with a 0.5 than you can with a 2 millimeter. So projected focal spot versus effective. Every year I talk about this. I want to get rid of this slide because, one, it's not in the other textbooks. Essentially, because the beam is diverging, the effective focal spot is actually a little bit different depending on where the radiation kind of hits. So that definition of the effective focal spot being from the perspective of the image receptor is true, but you can look at it as if there are multiple perspectives, right? Depending on who gets hit. Not incredibly important. However, what I do want to note that I kind of alluded to before, this part that's underlined here, the spatial resolution may be limited if the pixel size is larger than the effective focal spot. So what this means is, and we talk more about this next year in the next course. By the way, the book doesn't change, so you don't have to get a new book. We just literally go to the next chapter. If your pixel is, let's say, a millimeter, that means you can only resolve an object that is 1 millimeter or larger, nothing smaller. Now, if you're able to have a focal spot that gives you an effective focal spot that gives you 0.5, but your pixels are 1, then it doesn't matter. You won't be able to resolve that object, right? So if the pixels are bigger than the effective focal spot, they will limit you. Let me give you another example. If the object is 0.6 millimeters and the pixels are, let's say, 0.7, and the effective focal spot is 0.5, you might think, oh, the effective focal spot is 0.5, the object 0.6, I should be able to see it. But no, you can't, because the pixels are larger. They're 0.7. So if the pixels are bigger than the effective focal spot, you can't see the object. So good news is pixels are pretty small, right? They're usually sub-millimeter. So hopefully our pixels don't limit our effective focal spot. Okay, anode heel. So you've probably heard about this before, right? The simple definition is that you have a higher intensity towards the cathode side and a lower intensity towards the anode side. So if you look at this, if we were to kind of draw a line under the word anode, and we're producing photons along this line, they're going down. If you look the left side where you have this heel, right, it's potentially going to get reabsorbed and never make it out of the tube. So everything towards the left, that intensity is going to go down because some of your photons get killed before they make it out. But on the right side of the anode, I mean, yeah, you could still get reabsorbed, but look at all of this over here, all this empty space compared to what's to the left of it. So if you have photons being produced towards the cathode side, you are likely that more of them will escape. So the rule makes sense. You have a higher intensity towards the cathode side and a lower intensity towards the anode side. I was telling the last class, somewhere I have a diagram that has percentages on this. And it is quite dramatic. I think it's about a 25%, maybe more difference between the cathode side and the anode side. It's pretty significant. So the rule is if you have an object that has a thicker versus a thinner side to it, like the example we'll see is going to be the femur. So you have the head of the femur, which needs more penetration, is thicker, bigger than the distal portion of the femur as it, gets towards your knee, that you should put the thick part of that object towards the cathode side to take more advantage of that higher intensity. You'll see the images in just a moment. But what I will tell you is nowadays, this is almost gone. I'm just waiting for them to remove this because generators have gotten much higher. So the efficiency of creating photons to begin with has increased. Two, the built-in algorithms that adjust contrast and fix brightness, etc., are really good. It's very hard to duplicate the anode heel effect. Fourth, if I'm up to four, the effect of anode heel changes depending on how large the field of collimation is. So remember, if you have a smaller field size, you're not going to see the anode heel effect as much. So all the examples that I've ever used and have ever heard of have involved long bones, humerus, femur, tib fib. Do you have anode heel effect to a certain extent on a wrist? Yes, but you're not going to see it. It's not going to be noticeable that one part of the wrist is kind of more underexposed versus overexposed than the other part of the wrist. Just doesn't happen, right? I'm going to skip this one and come back to it in a second. So this is kind of what I'm talking about. This is an example of a femur where the head of the femur is placed on the anode side of the tube versus the cathode side of the tube. And in this example, you can see that when we place the much thicker portion of the, in this case, I think it's the humerus, actually. Yeah, you know, in the last class, no one caught it. I kept saying femur. It's the humerus, but no one said anything. In any case, would have been basically the same thing. So here, this looks better. Why does it look better? Because there was a higher intensity. There were more photons on this side. We didn't change the technique. We didn't change SID. We didn't do any of that. It was just the difference between the patient's head when you're facing them, like towards your left, and their feet towards your right versus the other way around. All we did was switch. And it is a big difference, right? Where the head of the humerus here is over the anode side, where there's less intensity, literally less photons, maybe 25% less photons. We don't see it. So the idea, just to read it out to you again, the best practice is to place the thicker portion of the patient or the part towards the cathode side of the tube to take advantage of that higher intensity, right? Anode heel also occurs more at a shorter SID. There's really nothing we can do about that. I mean, we're not going to increase our SID beyond 40 unless it calls for 72. And larger field size. So when I did this in the lab, and I don't know if we do this next semester or not, but what I did is we have digital dosimeters that literally numerically keep track of the dose. Because if the intensity is higher on one side, the dose should be higher. So what I did is we took 2 exposures. We opened the collimator all the way up as much as it would go. And then we placed this box, which is the dosimeter. For one exposure, we placed it as far as we could go towards the anode. And then we took a second exposure and placed that same box as far as we could go towards the cathode. And we did see that the cathode gave you more radiation. Literally, the numbers went up. Nothing was changed, only the position of the dosimeter, right? KV, all those things, SID, all those things were the same. So we were able to prove the anode heel effect in terms of more radiation, higher intensity. But you really nowadays can't see it on an actual radiograph. So this is eventually going to go away. By the way, you can tell which side is anode and cathode because on the tube, it should be labeled, right? One side should have a little plus sign. The other side should have a little minus sign. Plus is the anode, minus is the cathode. And the anode heel effect is increased, right? When the angle goes down, which is kind of unfortunate because we said earlier, when the angle goes down, we get a smaller effective focal spot. So Gabriel, what are you doing in my presentation? You're leaving like little trails.
Sorry.
It's okay. I don't know how to get rid of that stuff though, I think. Anyway. As long as you don't like delete anything. So anode heel is also increased. This part I understand is increased with a larger focal spot, right? Because a larger focal spot means the anode kind of has an increased amount of thickness to it. Again, this is really hard to see. You could tell these are old images. I think they were done with film. All my labs used to work really well with film. Now the digital capabilities of things I don't want to say have taken the fun out of things, but they do correct for a lot of stuff. Okay, sort of to sum things up here, the size of the focal spot is inversely proportional to spatial resolution, which means, right, focal spot down, spatial resolution up, right? We know this already. And it's proportional, not just inverse. So that means if the focal spot is cut in half, then the spatial resolution will double. There's no effect on magnification, because the only things that change magnification is if we have a change to SID, OID, SOD, those things. Okay. That blur, penumbra, is increased when focal spot increases. And when that penumbra goes up, the object kind of in the middle kind of shrinks. That object in the middle, kind of like the hole in the donut, is the umbra, right? So you have umbra is sort of the object, but you could kind of think about it as the penumbra kind of extends towards the edge, but also goes inward towards the object, towards the umbra. Thus, the umbra gets smaller. So if we look at this last diagram for the semester, can you believe it? You guys have gone so far and know so many cool things, so many new words too. We have a larger focal spot size increases penumbra. Let's see. This is a larger focal spot. This is the smaller one. This is our penumbra. Yeah, look at this compared to the one on the left. So larger focal spot increases penumbra, but actually shrinks the umbra. So yeah, here's our umbra, much smaller than this one here. So we don't like penumbra because we don't want our umbra shrinking. Therefore, as it says, larger focal spot size increases unsharpness, but it's not due to magnification. Note that the penumbra is directly proportional to the focal spot size. We've said that a couple times. So in other words, tripling the focal spot will triple the penumbra. You know, I didn't measure these and try to match it up, but I'll take the textbook's word for it. Again, it all comes down to utilize the small focal spot whenever possible, because the large focal spot will give you more penumbra, meaning your umbra gets smaller and your spatial resolution goes down. Right? We only use it because we have to. And folks, that is a wrap for fall of 2024. Any questions I can entertain on anything related to this course, to next semester, to clinical, to the final, what have you? Because I am not coming in until final exam morning.
I have a question.
Mm-hmm.
I want to look back on my old tests and see what I got wrong so I can study it. Can I schedule something like that?
Not anymore.
Okay.
Sorry. All that stuff, all those many scantrons plus previous years of many people are not, I couldn't fit them in my apartment. So they are all on campus.
Oh.
But if you have a question about something, you can email me. And if your question is interesting and I give you kind of a detailed answer, I won't out any student that does that, but I'll give the answer to like everyone if I think it's helpful. I have done that before. So yes, we had a whole lot of time. Yes, I was sick a little bit, but I know some people did manage to see me over the last few weeks. Questions?
Yes, Professor, I have a question regarding the focal spot, right? It
Mhm.
does it only affect the spatial resolution, the penumbra, but it has nothing to do with contrast. There's no effect on contrast. It's more has to do with spatial resolution.
That is correct.
Okay. Yeah.
Focal spot is just resolution, no magnification, no contrast.
Great. Okay.
Yeah. Speaking of that, I don't know if I mentioned this earlier. Don't read into the questions on the final exam, right? People tend to think, like I showed that image before of the anode heel effect and the head of the humerus. Some students might read into that and say, oh, you should just increase KV. You'll penetrate more, and then you'll see the head of the humerus. Yes, that is something that you might do, but if the question doesn't ask you what you should do, just answer the question straight, as crazy as it might sound, right? Don't read into it, if that makes any sense to you guys. You don't have to put your picture on to ask a question, by the way, if anyone's shy. I can hear you. No, people are leaving already. Okay. If you have any questions, let me know. Good luck. My test is the first one, which may be good for people, kind of get mine out of the way. And then things get a little bit easier for people. Although protection is challenging, usually patient care is not too bad. All right, everyone. I will post this video in a couple hours. Someone have a question?
Yeah. It's not
Yes.
about school. I mean, it's not about the class though.
Okay. I'm going to stop
I was just wondering,
recording.
do you like chocolate or cookies more?